Chapter 7, Introduction to Sampling Distributions. In this video, we'll learn how to calculate the mean and standard deviation for the sampling distribution of the sample proportion, p-bar. Another common measure that we often use in business statistics is the proportion. For our population, when we're trying to find the proportion, it's the fraction of values in a population that has a specific attribute. Similarly, if we wanted to know the proportion in a sample, it's also the same idea in that it's a fraction of items from the sample that have a particular attribute of interest. So we can see here in our formulas that they look very similar, but the capitalization or symbols used denote whether it's a population or a sample. So here we have little p, which means our population proportion. To find the population proportion for any particular attribute we're interested in, it is big X, or the number of items in our population that has that attribute of interest, divided by our big N, which is our population size. Similarly, with our sample proportion, if I were to pull a sample out of the entire population I was interested in, this would be denoted by P bar. And to calculate it similarly, we'll take our little x, or the number of items in our sample that has the attribute of interest, divided by our little n, or sample size. So it's important to know the difference between little p, which means population proportion, and p bar, which is our sample proportion. It's common to mix the two up, so just make note. Here are some examples of proportions. Say we wanted to know the proportion of customers who use a 20% coupon at Bed Bath & Beyond. In this example, the attribute of interest is whether or not the customers use a 20% coupon. In our second example, this is the proportion of Americans who own a home. Again, our attribute of interest is home ownership. In our third example, we have the proportion of MiraCosta students who eat at the cafeteria on campus. The attribute of interest here is eating at the campus cafeteria. And our fourth example is the proportion of defective phones. In each of these, we can find the proportion of our attribute of interest by taking the number who have this particular attribute divided by our population size or our sample size, depending on if we're looking at populations or samples. Similarly, when we learned about the sampling error for mean, here is the sampling error for a proportion. Again, we will determine the population proportion, find our sample proportion, that's p bar, and then compute the sampling error by taking our sample proportion minus our population proportion. Recall that this sample always comes first in our sampling error and then is subtracted by our population. Some things to note: when we're working with the sampling distribution of p bar, the best estimate of our population proportion p will be our sample proportion, or p bar. Any inference we make about how close our estimate is to the true population value will be based on the distribution of the sample proportion p bar. So recall when we learned about distributions, this is the way our curve looks. And in this case, our distribution is binomial, because for a proportion, they either have the attribute or they don't. Recall with the binomial, we're looking at two possible outcomes. Another thing to note is the sample size as it relates to our sampling distribution for p bar. When we talked about sampling distributions for the mean, or x bar, the conservative rule of thumb was we needed a sample size of 30 or more. When we're working with proportions, to determine if our sample size is large enough, we use the following two formulas, where we take our n, our sample size, times our p, the probability of success for our outcome of interest, and that should be greater or equal to 5. And we will plug in the same n and the p in our second formula, where we'll take 1 minus p and then multiply that by our sample size, and that should be greater or equal to 5. So as long as both formulas are satisfied, then we know we can use the normal distribution to approximate the discrete binomial distribution. In other words, we can now use Appendix D to find the probability of something occurring. Here are the two formulas, our mean and standard error for our sampling distribution of our sample proportion, or our p bar. So here we see our mean for the sampling distribution. It's essentially just our p, or the population proportion. You'll be given this in any problem you see in the textbook or on an exam, for instance, or in a real-world example. And the standard error is this formula where we're going to take the square root of our population proportion times 1 minus our population proportion divided by our sample size. Earlier in the chapter, we learned several theorems that allowed us to apply the sampling distribution of the mean, or x bar. Similarly, Theorem 5 takes all the pieces that we've just discussed and it allows us to work with the sampling distribution of p bar. So regardless of the value of the population proportion p, aside from p being 0 or 1, the sampling distribution for our sample proportion will be approximately normally distributed, with our mean and our standard error as long as our sample sizes are sufficiently large. And note that the approximation to the normal distribution improves as the sample size increases and p approaches 0.5. Just like when we worked with the sampling distribution of the mean, we can also convert our sampling distributions of p bar into z's. So here is the formula to convert our p bar into a z. You'll take our sample proportion, or p bar, minus our population proportion, and we'll divide it by the standard error. Again, I've listed down here below the formula for our standard error. That's our population proportion multiplied by 1 minus our population proportion, divided by n, and then square root the entire thing. Let's look at an example. So a big problem for taxpayers has been the recent increase in fraudulent tax returns being filed with the IRS in the name of taxpayers. So suppose the IRS believes that 15% of all taxpayers will be affected in 2016. Assuming the true proportion of taxpayers who get hacked is 0.15, what is the probability that more than 40 in a random sample of 200 will have been hacked? In this case, our attribute of interest is people who get hacked on their tax returns. Note in this word problem, we have the population proportion provided to us twice in two different formats. Here, the population proportion is listed as 15%. How we know it's the population proportion is in the context of the story, because as we see it says 15% of all taxpayers will be affected in 2016. So our population of interest here is taxpayers in 2016. Our population proportion is given to us again in the very next statement, assuming that the true proportion of taxpayers who get hacked is 0.15. And remember that 0.15 and 15% mean the same thing, they're just in different formats. Whenever you see in the word problem, if it's in a percentage, you'll want to convert it into decimal format in order to work with our formulas. So we have our p at 0.15, which is our population proportion, and we also need to calculate our sample proportion. So in our problem, we want to look for where's our sample. In this case, it is at the very end of our statement where we're looking for 40 in a random sample of 200 because the attribute of interest is those that get hacked. So we'll take x divided by n. Our attribute of interest is the number of people who get hacked. That's 40, and we'll divide it by our sample size of 200. So when we divide 40 by 200, we get a sample proportion, or p bar, of 0.2. In our question, when we write it as our event of interest, we're essentially saying that we want to know the probability, that's a big P, of our sample proportion, that's our p bar, will be greater than 0.2. Because recall in the statement here, it said, what is the probability that more than 40 in a random sample? But I'm not going to write 40 in my mathematical statement. I'm going to write the proportion, in this case, proportion of our 40 over 200 at 0.2. So let's look at what this looks like in a normal distribution, thanks to Theorem 5 that says we can now calculate the sampling distribution for a proportion through our various components. So if I were to draw my normal distribution, where we have our population proportion of 0.15, or 15% of all taxpayers in 2016 will get hacked, according to the IRS. And then in our sample proportion, where we took 40 divided by 200, that gave us our sample proportion of 0.2. And in our story, what we're interested in is the probability that more than 0.2 will get hacked. So there's our event of interest there. So all we've done is taken the pieces from our word problem, put it into a visual representation of our normal distribution. But thanks to Theorem 5, if I know something is normally distributed, we want to convert it into z-values
and use Excel to find the probability of our event of interest. So using our formula here, we will first take our sample proportion of 0.20, and we found that by dividing our x over n, which was 40 over 200. Then we will subtract our population proportion, which was given to us in the story. This here will represent our sampling error. And then in the bottom, this is our standard error. And so our P here, as you can see, it's the population proportion that's given to us in the story. So we'll plug in the 0.15 and then multiply that by its complement, or 1 minus P, which is 0.85. In other words, this 0.15, this is the proportion of the population that get hacked, and 0.85 is the population of the proportion that doesn't get hacked. We then divide it by 200, that was our sample size, and then square root the whole thing to get our standard error. Once I have my sampling error on top and my standard error in the bottom, I then divide the two from each other. Order of operations matters, so be careful. That'll give us a z-value of 1.98. And here I've got my distribution on the side. If I draw my z-value of 1.98, it'll be over here on the right, because recall that our center z here is 0. It's like a starting point. And so 1.98 is bigger, it's going to be on this side. And recall in our problem, we want to know the probability that more than 40 out of 200 people get hacked. So we're looking for greater than 1.98, which is in this little shaded area here. So we'll go ahead and use Excel to find our desired probability. Again, the question I always ask myself is our event of interest greater or less than the z-value? In our story, we were asked for greater than. So here I'm writing out the probability that our z is greater than 1.98. And then I'll go ahead and use our formula of 1 minus our norm.s.dist, plug in my z-value, and plug in true. This is the same process we do for the mean. So this formula works for both means and proportions, as long as you solve the z-value by hand first. So let's go ahead and look at Excel and see what happens. So here's the formula for whenever we're looking at greater than or equal to some variable. And so I'll type in equals 1 minus norm.s.dist, parentheses, our z-value was 1.98, comma, true. Close my parentheses and hit enter, and I get 0.0239. In other words, the probability that more than 40 people get hacked in our sample of 200 is 0.0239, or 2.39% chance. So it's a very small chance that more than 40 out of 200 will get hacked.
Now go ahead and pull out your worksheet if you don't have it already in front of you, and let's do another practice problem. This is number 57 from our textbook. Say that 10% of U.S. engineers, this includes electrical, mechanical, civil, and industrial, are women. Suppose a random sample of 50 engineers is selected. Part A asks, how likely is it that the sample of engineers will contain 8 or more women in these positions? So our first step is we want to determine our population proportion. What's our P? In this case, it's given to us in the story at 10% of U.S. engineers. How I know this is the population is because we're talking about the United States as a whole, U.S. engineers. So our P is 0.10, or the decimal form of 10%. In step 2, we need to calculate the sample proportion we're interested in studying. So that was given to us in part A in the question, where it asks how likely is it that the sample of 50 engineers will contain 8 or more women. So in this case, our attribute of interest is whether the engineer is a woman. So our X will be 8, and our N is our sample of 50. Thus, our sample proportion, when we take 8 divided by 50, is 0.16. In step 3, we want to define the event of interest. Again, this is given to us in part A, in that we want to know the probability that there will be 8 or more women in our sample of 50 engineers. Since we've already calculated our sample proportion in step 2, we will write our event of interest as the probability that our sample proportion will be greater or equal to 0.16.
So in step 5, we're going to convert the sample proportion that we found in the previous step into a z-value. So I'll go ahead and plug in first our sample proportion of 0.16 and our population proportion that the story told us, our little p, of 0.10. Note that this top part of our formula represents the sampling error. In the denominator, or in the bottom part of our formula, this is our standard error. And so, as you can see here, our population proportion is what we will plug in. So I'll plug in my 0.10, then I will take the complement of it using 1 minus 0.10, and my sample size of 50. Then I'll go ahead and simplify, and I always work in components to avoid errors. I will first subtract our sample proportion by the population proportion to get our sampling error of 0.06, and then I will solve our standard error and get 0.04242. Now I will then divide our sampling error by our standard error, and that'll give us a z-value of 1.41. And then in step 6, we can use Excel to find the desired probability. So here, because we're interested in finding a greater than statement, I'm going to use this formula here of 1 minus norm.s.dist, plug in our z-value, type true, and you'll get 0.0793. Let me go ahead and show that in Excel as well. So using our greater than formula here, I'll type in equals 1 minus norm.s.dist, parentheses, 1.41, comma, true. And that's how I got the 0.0793 for our solution. In other words, there is nearly a 0.08 or 8% chance that the sample would contain 8 or more women. Now, I want to highlight when we explain our statistics and we say it's going to have 8 or more women, we want to name that this is out of the sample, because if you don't say the sample, then our decision makers, our audience, the people you're presenting to won't know, is this 8 out of 100, 8 out of a million, 8 out of 50? In this case, our sample was of 50.
Let's do part B. Same story. 10% of U.S. engineers are women. In part B, how likely is it that a sample of 200 engineers will contain fewer than 5 women in these positions? Again, step 1 is we want to find our population proportion. Recall that's given to us in our story at 10%. So I'll write this as a decimal, 0.10. In step 2, we want to calculate the sample proportion. So we're going to look at our pieces in part B. In this case, we have our sample of 200 engineers, so we'll put that in where our n is, and we're interested in knowing the chance that it will contain fewer than 5 women. So our x is still our attribute of being a woman, and here the number specifically is 5. So when we take 5 divided by 200, our sample proportion is 0.025. Do not round. In step 3, we want to define the event of interest according to our question B. In this case, we want to know the probability that our sample proportion is fewer than 0.025.
In step 5, we'll convert our sample proportion to a z-value. So now I'll go ahead and plug in my sample proportion that we solved on the last slide of 0.025 minus our population proportion of 0.10. And then for our standard error, we'll plug in our population proportion and our sample size of 200. Note that in this part of the problem, we've changed our sample proportion as well as our sample size. So you want to make sure that you use the correct data from the problem. Solving my sampling error, I will subtract the top 2 numbers, and I get a sampling error of negative 0.075. And solving for our standard error, where I will take 0.10 times 0.90, divide by 200, and square root all of that to get 0.0212. And then I will take our sampling error and divide by our standard error and get negative 3.54. Now in this question, we're asked the chances of less than some value. So we're going to use this formula, equals norm.s.dist, plug in my z-value of negative 3.54, plug in our true, and you'll get a probability of 0.0002. And let me go ahead and show that on Excel as well. So here's our formula right here when you're looking for less than some value. So I'll type in equals norm.s.dist parentheses. Our z was negative 3.54, comma, true. And so our probability is 0.0002. So it's nearly zero chance that our sample would contain fewer than 5 women. If you have any questions, just let me know.